So polarity refers to when two atoms are unequally sharing electrons. And if you remember, we determined the polarity using electronegativities. And fluorine is top dog, it's 4.0. And as you move away from fluorine, the electronegativities drop off. We don't even report electronegativities for noble gases because they don't really make bonds. Yes, we did just learn that it's possible, but it's not possible in like everyday life to make a noble gas do something. So they're not going to be sharing electrons anyway. So you gotta, and if you need to know the specific electronegativities, I'll give them to you. Remember our continuum scale, a difference of 0 to 0.5, we consider that to be nonpolar. A difference in electronegativity between the two atoms between 0.5 and 2, that's polar. And if you're greater than 2, you're probably ionic if you're greater than 2. Okay. So, for example, if I look at the C to O bond, this is a pretty darn polar bond. Carbon, if you look up its electronegativity, 2.5, oxygen, 3.5. That falls in this polar range, definitely polar. Oxygen is going to hog those electrons. So those electrons are going to spend way more time on the oxygen than they do on the carbon. And what is that going to do? Well, that's going to cause the oxygen end of this molecule to build up a slightly negative charge. And the carbon end of this molecule is going to build up a slightly positive charge. Remember, we can represent that with a dipole moment arrow as well. So this bond is polar. It's a very polar bond. But, okay, just because a molecule contains polar bonds does not mean the molecule itself is polar if it's a symmetrical molecular geometry where the polar bonds will cancel each other out. Here's what I want you to do. I want you to draw carbon dioxide. Go ahead and draw carbon dioxide, and I want you to draw it with the right shape. Why don't you give me the name and the bond angle as well? Go ahead and do that. All right. So 4 plus 12 equals 16. Oh, I guess I should go in too fast here for you. Let's work our way through it. Uses up 4, got 12 left, 2, 4, 6, 8, 10, 12. It's a double uh-oh. We're double bonding both of these bad boys. There we go. Now, here's why we're doing this. We just said carbon and oxygen are going to unequally share electrons. So if we look at the carbon to oxygen bond on the right, oxygen is going to hog those 4 electrons because it's a double bond. It's 4 electrons. Oxygen is going to hog those electrons. So delta minus, delta plus on the carbon. This carbon to oxygen bond, oxygen is going to hog those electrons. Delta minus on the oxygen, delta plus on the carbon. But yes, this molecule contains 2 polar bonds. This guy's trying to tug that way. This guy's trying to tug that way. But what happens in a game of tug of war where both sides are equally matched? Well, in a game of tug of war where both sides are equally matched, nobody's going anywhere. Nobody moves. So when you have a symmetrical molecular geometry, okay, where the bonding groups are identical, this molecule contains polar bonds, but it is non-polar overall. The electron domain 2, linear molecular geometry, if both bonding groups or X's are the same, then the molecule will be non-polar overall. Pretty awesome. Polar bonds, non-polar molecule. What does that mean? This would not dissolve in a polar solvent. Okay? Nope. So if you had liquid carbon dioxide, or solid carbon dioxide dry ice, it's not going to dissolve in a polar solvent like water. Okay. Yeah. Any symmetrical molecular geometry can do this as long as the X groups are the same. So if we take a look at the Vesper molecular geometry sheet, and I would actually recommend that you label these. Let me get the text thing up. This linear molecular geometry, this is the one we just did, this has the potential to be non-polar. Now, if the X groups are not the same, if it's HCN, that's linear as well, but they're not, then that's going to be polar. Okay. All of the X groups have to be the same. Same thing with trigonal planar. Trigonal planar has the potential to be nonpolar. Okay. If the X groups are all the same, then they're all going to tug 120 degrees away from each other and they're all going to cancel each other out. In fact, if you go down through the lone pair, zero lone pair column, these are all nonpolar if the X groups are the same. If the X groups are the same, then all of the first shapes in the geometries, they are all going to be nonpolar. These are all nonpolar. If you put one lone pair off of the central atom, well, one lone pair is going to automatically distort the bond angles. So the shape will no longer be symmetrical. So anything with a single lone pair on the central atom is automatically polar. So these shapes, everything in column 1 with one lone pair on the central atom, these are all polar molecules. By default, doesn't matter what the X groups are, they have to be polar. And now, if we look here, this is a very important geometry in terms of molecular polarity. This is domain 4, 2 lone pairs. This molecule is really distorted. Okay, these X groups are not going to cancel each other out. That is a very important polar geometry. Why is this one super duper important? In fact, it's so important, I'm going to circle it. This is the geometry of water. Water is a domain 4, 2 lone pairs, right? So that's water's geometry. So you got to know water is polar. This T shape, polar. Those lone pairs are distorting the bond angles. Even if they're all the same, doesn't matter. Square planar, non-polar. It's super duper special. Let's talk about it. Whoops, uh-oh. Let's talk about it. These X groups are all, because the two lone pairs cancel each other out, they are a perfect 90 degrees apart. If all 4 of these X's are the same, that's going to be a non-polar molecule. And finally, this linear guy over here, same thing. This guy can be nonpolar if the X groups are the same. It can be nonpolar if the X groups are the same because the lone pairs cancel each other out, no distortion in the bond angle, and it can be a perfect 180 and be nonpolar where these guys can cancel out. So all the ones with NPs, these guys can contain polar bonds, but be nonpolar overall, which is pretty awesome. It's pretty impressive. Cool. Any questions on molecular polarity? So this now, folks, is pretty much what you want to try to memorize or get as much of it in your brain for Tuesday, right? You want to have this sheet memorized, okay? And you want to be able to determine if the geometry can be polar or non-polar. So yeah, now that we've added the non-polars and polars to this, this is now complete, and this is the shape. This is kind of what you want to do. If you are going to take organic chemistry, my goodness, do you need to know domains 2, 3, and 4 like the back of your hand? You don't really need to know domains 5 or 6 if you take organic chemistry because carbon is in period 2, so it can't exceed the octet rule. So that's why you're stuck with domain 4 only and you don't get down into domains 5 and 6. But my goodness, are those, what is that, 6 shapes? They are ridiculously important when it comes to organic chemistry.